Hello, thank you for attending my presentation on a serverless programming model for heterogeneous hardware accelerators, which we call Kernel-as-a-Service. It works a collaboration between our group at TU Berlin, Mobile Cloud Computing Group, and a bunch of researchers at Hewlett-Packard Labs, where I was on internship last year. Currently, you might have seen this, we talk a lot about Moore's law, and Moore's law being in decline. So the general notion of every 18 months, due to advances in transistor technology, we can double the compute power of regular CPUs. Now, this is declining because we're hitting physical limits, and it's forcing us to specialize somewhat in our hardware department. So today, we mostly use CPUs for all of our workloads, but we're seeing a trend towards more heterogeneous hardware. We already have GPUs used for machine learning, but there will be even more heterogeneous hardware in the future, from tensor processing units, FPGAs, even quantum processing units, alongside our CPUs that we know today. And this is leading to a few problems in how we allocate resources, how we program resources. Now, the first challenge is that this resource disaggregation, as we move towards heterogeneous resources, will require new programming models. If we look at the traditional IaaS model that we know from the cloud today, where you rent a whole node for a specific amount of time to do your computation on, if you have heterogeneous resources on that node, let's say CPU, GPU, a TPU, and an FPGA all on the same host, as you have a heterogeneous workload, let's say a workflow, could be a single workload, you will use different parts of those resources over time. Might start with some CPU work, then move on to GPU work, and so forth until a new tenant will be on that node after your work is done. And of course, renting everything for a specific amount of time leads to a lot of hardware sitting idle. We call this time sharing because you are sharing a node only in time, and you don't, share in space where you share between other tenants on the same node. Additionally, a second challenge is that accelerators are becoming bigger. Now, this might seem like a nice thing because we can run more things on an accelerator, but the thing is, look at an A100 GPU from NVIDIA, which isn't even the latest generation of their enterprise GPUs. That has 108 streaming multiprocessors. So these are parallel processors computing your workload. If we do inference using Meta's Llama 2 model, which is comparable to ChatGPT, but you can run it locally, we see that even this advanced workload uses only a fraction of the available multiprocessors on our system, so a maximum of 20. So again, you have a lot of hardware sitting idle. Even though you're investing in the best hardware out there, you can't really use all of it at the same time if you use this time sharing model and you use your complete accelerator for a specific workload for an amount of time before you free it up to run the next workload. The third challenge that we saw was that shorter tasks are generally at a disadvantage in heterogeneous computing. So let's look at this little workflow. It takes a number, an image of a written number, does some image preprocessing, does grayscale conversion, and some sampling, and then does ML inference on that. So think of the MLS data set, and can tell you which number it is. But this is a fairly simple task. And you might think, okay, my preprocessing can run on CPU. It's more or less general, it's fairly short. For a grayscale conversion, this is supposed to run even better on FPGA because you're doing a lot of the same things in parallel and you can optimize your hardware to run your specific algorithm. And for ML inference, of course, we want to run that on the GPU. So this is our little workflow. And if we do heterogeneity, we run everything on a specific accelerator to get the best out of our available hardware and the best performance for our workflow. What happens in practice, however, is that a CPU-only implementation of this workflow will run much quicker than a heterogeneous execution. And this isn't necessarily because our FPGAs or GPUs aren't tuned or good enough, or that our CPU is too good. No, actually, one of the reasons if you're doing trivial, naive implementations of these workflows is that there's a lot of overhead in initialization for accelerators. Think of this kernel on the FPGA, for example. So we call this little task a kernel because it's an isolated task running on an accelerator. And you see that there's about a 66% overhead, not including the data copy, which is fairly quick, but just doing initialization. So that's not putting the IP on the FPGA, which can take a long while, but there's nothing we can do about that. But it's only from a program setting up the channels and preparing the data transfer and setting up our FPGA to run our workload. For GPUs, it's even worse. So you have a lot of init time to boot CUDA, for example, the CUDA API to use that. This is all in Python. And even though a kernel can run much, much quicker on the GPU than on the CPU, even including data copy time, in total, we have a longer task completion time. And I should note that, of course, these init times are about constant regardless of task length. So if you do some ML training that takes 2 days, those 3 seconds of initialization time won't be an issue for you. That's fine. You will have much better performance on a GPU than on the CPU. And you might say, now, okay, we have these challenges that time sharing leads to idle hardware, accelerators are growing, overheads inhibit shorter tasks. And you might say there might be someone who's a GPU or FPGA expert in the audience, and they might say, oh, that's fairly simple to fix. You just increase your CUDA frequency, segmentize your kernel properly, you repartition your mix, which is fine if you're an expert in this. But I guess that the 99% of the audience who are not an expert on this will be unlikely to even tell which of these 4 things you see on the slide are even real and which ones are made up. We are missing a lot of knowledge broadly that hinders the adoption of more heterogeneous resources. And of course, we know as middleware researchers in general in distributed systems, as we increase the amount of abstraction through middlewares, we can also increase efficiency, developer productivity, and general adoption of some systems or some infrastructure. And of course, we know this, so we thought, okay, can we come up with a middleware, some amount of programming model that allows us to do finely grained sharing of accelerators, both in time, so one workload runs after the other, but also in space, running workloads in parallel, and without that costly overhead. And here we think one of the most promising models that we can adopt here is serverless computing or function as a service. At its core, if you're not familiar, the benefits of serverless and function as a service is that there's an increasing amount of sharing of the underlying infrastructure between applications and tenants. So that can abstract from a pool of resources used at the same time by different services and application services and tenants, dynamically allocate resources. So if you need something, it's just allocated for you. You don't pay for something you don't need. And it allows you to fine-grained sharing of resources in space and in time. And of course, if you configure your application to be serverless workflow, it allows for flexible reconfiguration. If you have a task that follows another task, you can simply add a step in the middle without having to touch the first 2 applications. The general fast architecture, this is a bit simplified, is you have some fast server that acts as both a gateway to clients using event-based invocation. You then have a developer specifying the applications through an API. You have handlers for your function code. So you have function 1, a handler is booted on invocation, and the fast server can invoke that function, and resources for that are allocated on demand. And then, of course, you have some isolation backend. Usually this is a container engine, but there's some other approaches as well. But the main part is that each of your handlers is isolated from all other workloads, and resources are allocated on demand then. There's been some great work on adding accelerators to function as a service. So this is, I can recommend a few papers to you, but in general, what they do is you have your container, you just add an accelerator to the container, and then your workload can use that accelerator, that additional hardware. But that doesn't really allow sharing in time and space, and it's more like an add-on to Lambda. Instead, we are proposing the other direction. We are saying, how can we add the ideas of fast to accelerators to achieve the same benefits of serverless computing that we see in the cloud today on heterogeneous resources? So we have that sharing, we have that multi-tenancy, etc. And this is where Kernel-as-a-Service comes in. The basic architecture, like in fast, is that you have some server. In our case, it's still running on the CPU because We still have, some organizations and algorithms for resource scheduling. Those can run fairly well on the CPU. You register your kernel code. It's wrapped in a wrapper function similar to serverless, but your kernel code, your task, your actual code is actually running on an accelerator. So we don't say we run CPU workloads. There might be some CPU components to your kernel code for data movement, data preparation, but your kernel is supposed to run on an accelerator. And then you can simply invoke your kernel with some input data, you make it output data from your accelerator. And in this way, you can even compose workflows where you use different accelerators over time. All you really need for this to work is some sort of some form of isolation backend. Like containers on general purpose hardware, we need some isolation backend to segmentize basically our kernels running in parallel to achieve isolation between services. Here's a GPU implementation. You'll find more details in the paper. Basically, we are doing, in this case, isolation using NVIDIA multi-process service, which allows just that. We have a client which can access to a cache server specific kernels running on the GPU. We can do resource allocation on the fly as we come in. And we also have some GPU memory, which is also isolated using NPS. We ran a bunch of tests, evaluation. You'll find more details in the paper, including warm and cold start, profiling, parallelism, throughput, energy, etc. It's a lot of numbers. You'll find all the results in the paper, so you can have a detailed look. In general, the conclusion is this works well, even with today's hardware, but there's additional work needed that I will get to at the end. We didn't stop there, however, because we said we wanted to target heterogeneity, and having just one accelerator isn't really heterogeneous. Instead, we also looked at more prototypes for all the accelerators basically that we could get our hands on. So this is NVIDIA GPUs using NVIDIA LPS as an isolation backend. We tried it on Xilinx Alveo FPGAs, data center FPGAs, which currently don't really offer an isolation backend natively, but there's some work out there from ETH, I believe, that can do that, but we didn't try it in this work for proof of concept. We also tried Google Cloud TPUs, which work fairly great. You can do isolation not on the chip, but you can isolate services on different chips. So there's always 4 to 8 chips on one TPU, and you can then run 4 to 8 workloads. And finally, we also ran it on IBM Quantum using the Qiskit runtime that they provide. Those results work. I'll add a note of caution. We believe it's actually running on quantum computing hardware. We did some simulation backend as well. But because of the way quantum computers are currently being offered to us, we don't have any way to really look into how they work and do any configuration on there. Does it work? Again, you'll find the results in the paper, but in general, yes, across all of these accelerators, looking at the initial example that I gave you, we can see that we have the same problems in overhead. We have the same benefits of programmability, abstraction, etc. But of course, feel free, and I encourage you, of course, to read the paper to find out more. Finally, to conclude, some conclusions. We believe that hardware specialization, so heterogeneous hardware, will reach every area of computing. It's currently limited to machine learning and maybe some HPC, but we believe that in the future, because of Moore's law declining, it will reach every area of computing, especially cloud computing and data centers. The adoption of serverless ideas, as we've shown, can help increase efficiency and adoption and productivity for developers using the same benefits that we know from cloud serverless computing today. And our prototypes have shown that this approach works even with the hardware we have today. Of course, in the future, as hardware will develop, we believe that hardware and software co-design will be the future. So you start with a simple prototype, you learn from that, you develop your software, you develop your hardware, and from there you have to constantly, the ladder system where one learns from the other, and we co-design our software and hardware. That's it for me. Thank you for your attention. If you have any questions, I'm happy to take them.